Welcome to the Strength of Materials 2 lecture. Today, we will be discussing continuous beams and Clapeyron's theorem of three moments. This theorem is essential for analyzing statically indeterminate beams, which are beams with more supports than necessary for static equilibrium. Continuous beams are structural elements supported on more than two supports. Now, let's discuss the diagram showing a continuous beam with two spans subjected to uniform loads. In this diagram, we have a structure consisting of two beams connected at a central support. The central support serves as a common support for both beams, while the ends of each beam are held by external supports. Each span of the beams is subjected to a uniform load, represented by a series of downward pointing arrows labeled load. In a continuous beam, the nature of bending moments varies along the length of the beam. At the midspan of the beam, between the supports, we observe positive moments, also known as sagging moments. These moments cause the beam to bend downwards, creating a sagging effect. Over the intermediate supports, we observe negative moments, also known as hogging moments. These moments cause the beam to bend upwards at the supports, creating a hogging effect. To counteract the positive bending moments, reinforcement, typically in the form of steel bars or rebar, is placed at the bottom of the beam sections. This reinforcement provides the necessary tensile strength, helping to prevent cracking and potential failure of the beam under load. By ensuring adequate reinforcement at the bottom of the beam, we can enhance the beam's load-carrying capacity and ensure its structural integrity. In the diagram, we see the continuous beam with reinforcement placed at the bottom where the positive moments are highest. This strategic placement of reinforcement helps in effectively resisting the tensile forces induced by the sagging moments. In continuous beams, different types of reinforcement are used to resist the bending moments that occur at various points along the beam. The first image on this slide shows reinforcement placed at the top of the beam at the intermediate supports. This top reinforcement is crucial for resisting the negative bending moments, or hogging moments, that occur at these supports, providing additional compressive strength and preventing structural failure. The second image illustrates the use of bent-up bars to further resist the hogging moments. These bars are bent upwards towards the supports, placing them in the tension zone where they effectively counteract the tensile forces induced by the negative moments. Bent-up bars enhance the beam's stability by providing additional tensile strength at critical points. Clapeyron's theorem of three moments is a fundamental principle used to analyze continuous beams. It relates the moments at three consecutive supports of a continuous beam to the applied loads and the lengths of the spans between supports. The theorem is often used to determine the bending moments in statically indeterminate beams, making it easier to design and analyze complex structures. In this problem, the beam is simply supported at points A, B, and C. There is a uniformly distributed load, UDL, of 6 kN per meter over a span of 4 meters from A to B, and there is a uniformly distributed load, UDL, of 10 kN per meter over a span of 6 meters from B to C. The beam has support reactions at points A, RA, B, RB, and C, RC. Since the ends A and C are simply supported, the support moments at A and C will be 0. And to find the support moment at B, Clapeyron's equation of three moments should be applied. The bending moment diagram due to vertical loads, here UDL, on span AB and span BC are also shown by parabolas of altitudes. We have seen that fixing moments on the ends of a simply supported continuous beam are 0. But in case of a continuous beam fixed at its one or both ends, there will be fixing moments at the ends. To analyze the continuous beam which is fixed at the ends by the equation of three moments, an imaginary support of 0 span is introduced. The fixing moment at this imaginary support is always equal to 0. We have a continuous beam. ABC of uniform section. Spans. AB is 4 meters. BC is 4 meters. Beam is fixed at A and simply supported at B and C. As beam is fixed at A, therefore introduce an imaginary 0 span. AA1 to the left of A, as shown in figure. The support moment at A1 is 0. and the extreme NC is, simply supported, so support moment at C is 0. To find support moments MA and MB, theorem of 3 moments is used. The bending moment diagram due to vertical loads, here UDL, on span AB and span BC are also shown by parabolas of altitudes. Applying the theorem of 3 moments for the spans A1A and AB, we have the equation in terms of MA and MB. Now applying the theorem of 3 moments for the spans AB and BC, we get another equation in terms of MA and MB. By solving above equations, we can determine the support moments at A and B. Here in this problem, following are the given data. Length of span AB, 6 meter. Length of span BC, 6 meter. UDL in the span AB is 2 kN per meter. Point load in BC is 12 kN. As beam is fixed at A and C, therefore introduce an imaginary zero span, AA1 and CC1 to the left of A and to the right of C respectively as shown in figure. The support moments at A1 and C1 are 0. Thank you.